All right, so now we're going to talk about the integral test and the p-series. So we have this geometric series test, okay, that we had from last time. So we know if r, which is this right here, this ratio, if is greater than or equal to 1, then it's going to diverge. Where if it's not, if it's between 0 and 1, if the absolute value of that ratio is between 0 and 1, then you can find the sum using this formula, right, where this is a 1. Now, we talked about the nth term for divergence on the previous lesson, but let's talk about it again. Remember, the nth terms test is basically the easiest thing is that if the limit of the sequence is not equal to 0, then the series is going to diverge, right? So, for example, in this one, let me look at my notes real quick. On this one, I could rewrite this one as this. Now notice that this part right here, this is r, all right? And r is between 0 and 1, right? The absolute value of this is between 0 and 1, which is good. So that means it's going to converge. So I know it's going to converge. So now I can actually to determine, now it's not really asking us to find the sum, but we can use the formula to find the sum completely. All right, so we're going to use that formula that says a1 over 1 minus r, which in this case, that's going to be, let's see, 1, that'd be 4/5. Yes. 4/5 over 1 minus, the r value is also, oh shoot, I messed up. This should be 4/25. So if I plug in a 1 for n, then I should end up with 1/5 times 4/5, which is 4/25. And then now this one right here is going to be 4/5. Okay. Now, when you do all the math for it, you're going to get that the infinite sum is going to be equal to 4/5. So again, it's not really asking us in this example to determine what it adds up to, but since this is a geometric series, we can. All right. Now on this one, we're going to try to, let's see, rewrite it. So in this one, what we can do is we can take the limit like we did before, the limit as n goes to infinity of just the sequence, which is this. All right, so we can use the nth term. And we could have used that. Well, the last one would have been a little bit hard to use on that, but nonetheless. So now we're going to use the nth term test for divergence. So remember, if the limit as n goes to infinity is not 0, which in this case is not, this is 5/2, and we know that 5/2 is not equal to 0. So that tells me automatically that this is going to diverge. Okay, so there's that for that. Now, it's basically, and this one is telling you the remainder of the chapter, we're going to cover a lot of these different tests and stuff like that, but we'll worry about that when we get there. Now we're going to quickly explore the integral series just to tell you that's basically introduction to the integral test. Okay, so if I were doing a right Riemann sum, which is what they want us to do here, basically I'm just plugging that into here, right? So that's the function right there. All right. So now we're doing a right sum from 1, by the way, we're starting at 1, from 1 to 5. All right, so because of that, that's what it's going to look like. Okay. And the height, since the width is 1 for all of these rectangles, then 1 times 1/4 is 1/4, 1 times 1/9 is 1/9. So it turns out that this is all of the areas. Now, when you add all those areas together using the right-hand sum, This is going to be approximately 0.464, excuse me. So now we're going to find the fifth partial sum. So we basically have this right here. So notice it's very, very similar, right? But really it's almost identical here, except for that one. And now if we take the integral of this right here, right? If we take the integral of that, we would get x to the negative 2. If I integrate that, I would have x to the negative 1 divided by negative 1, which essentially will give us this. All right, and what we find out is that the sum, the infinite sum between 1 and infinity of the sequence is equal to 1 plus the infinite sum between 2 and infinity. That's just a strange way to write it for sure. And let me make sure I'm writing this correctly. Let me check my notes here. So what that represents for you is that the integral represents the upper bound. Is the upper bound of the series. If the integral converges, as you take that integral to infinity, the series will also converge. Or it's bounded, I should say. If the if the integral diverges, meaning the integral goes to infinity or negative infinity, then the series is unbounded. And you don't really have to necessarily know this, but what will help you is this other thing called the integral test. Now where the nth test, that just basically tells you if something is divergent. The integral test can help you, all right? As long as the function you're dealing with is continuous, positive, and decreasing. All right, so again, the function must be continuous, positive, and decreasing. So now what that says is that when you have a sum, all right, what you can do is if you integrate that sequence, if you will, then if that's convergent, then the sum is also convergent. And if the integral is divergent, then the sum is also divergent. Now, remember, what this gives us is just telling us whether something's convergent or divergent, but it doesn't necessarily tell if it's convergent. It doesn't actually tell us what it converts or it converges on. All right. So, okay, so let's take a look. So for example number 2 on here, okay, we first got to make sure that it's positive, continuous, positive, and decreasing, which it all is. At worst, if you couldn't figure that out and you didn't have a calculator, you were taking a test, then you can take the derivative of this sequence right here and then figure out if that's positive or negative. Okay, so now what we're going to do for this next one is, now that I've determined that I can use the integral test, I'm going to go ahead and change this to an integral. And I'm just going to say that n is now going to be x. okay? And then I'm going to try to integrate this. Now, the hard part on some of these is basically how to integrate them, which I think we cover advanced techniques of integration. I believe those unit 7. So you might have to go back and check that out at some point. All right, so remember that this is called an improper integral. And you have to do that every time where you're taking an integral to infinity or negative infinity, all right, or both. So now, in this case, the hard part is to take the antiderivative of this. Now, you can look at a table and or do, let's see what you could do. You could probably do trig substitution. But if you do all of that without taking too much time on it, you would get this as your antiderivative. Okay, now you then have to plug this in. And by the way, for this, I normally have to look at the table or the graph because this is not something that I'm very familiar with or I'm used to it because I use it all the time. So normally you have, this would be your two answers. Now, the answer is going to be pi over 4. Now, remember, that's not the infinite sum, but what that tells us is because the integral converged, then that means that your sum is also going to converge. Okay, so that's all that we know. It doesn't really even matter that the answer is pi over 4. What matters is that it converged to a single value. All right, so let's go over to B. Let's see. First, make sure that it's positive, continuous positive and decreasing, which it is. Okay, so now we're going to take the antiderivative or the integral between 1 and infinity of x over x squared plus 1 dx. Now, on this one, you have to really sit there and think about how to do this, and hopefully you remember that you can use substitution. That's normally what I check first. If I were you, that's probably what I would check also. Where du is 2x dx. I don't need that 2, so I'm going to divide both sides by 2. All right, so I'm going to go ahead and write the limit because this is going to have an improper integral as, what do I want to say here? T, remember that you can use any letter that you want for instead of T. Of, let's see, I'm going to replace dx with 1/2 du. And this would be 1 over u, and between 1 and infinity. All right, nope, not infinity, between 1 and t. Let's see, you could, if you wanted to, kind of replace through the thing where I do this right here. I don't really know how useful that would be at this point. So let's not go ahead and do that. Let's just take the antiderivative and we'll plug that u back in and then evaluate it. All right, so this is going to be 1/2 the limit as t goes to infinity. Now the antiderivative of 1 over u is the natural log of u. All right, so now I'm going to go ahead and substitute back, instead of the natural log of u, I'm going to write the natural log of the absolute value of x squared plus 1 between 1 and t. So this is 1/2. And at that point, I'm going to go ahead and just plug in those limits. Sounds like my dog is whining outside my door. He probably feels like I have abandoned him. What a pansy. All right, so that should be 2. Yeah, okay. So remember, all that matters here, and really I did a lot of the work, but all that really matters to you is this going to converge. Now, no matter what you do on here, this is if you plug in an infinity for t, you are going to get infinity for that. So therefore, infinity minus the natural log of 2, whatever that may be, is still infinity. So this is going to diverge. All right, and I'm not talking about, yes, the integral diverges, but what I'm looking at is that the sum does not converge, meaning it does not go to a single value. So that's that, right? So this is a little bit more accurate, or is definitely more accurate than the nth term test, because yes, it can tell you something diverges, but it also tells you if something is converging, where the nth test may or may not, if it's equal to 0. Let's see. Do I want to explore this? I'm actually gonna skip this part. I can post the notes if you want to. I didn't quite see the point of doing that, so I'm gonna go straight to the P series. All right. So now the P series has that form that you see right there. Okay, where P is a positive constant. Okay, so remember that's a positive constant. And for p is equal to 1, the series, the sum, the infinite sum between 1 and infinity, 1 over n, which is the harmonic series. Remember, this is the one that we keep seeing a lot. You just have to remember that does not converge, or meaning is divergent. Okay, so for the p series, if you see something that fits, that is a p series, then you got to know that if p, which is the power here, all right, if it's greater than 1, then it's going to converge. If p is between 0 and 1, then it's going to diverge. And if it's exactly 1, well, then that's a harmonic series, which is also going to diverge. Okay, so just take a look at what we're talking about here, right? So, of course, some of these can fall under several different tests. On this one, for example, we can rewrite this as... So what I'm trying to tell you is that this may fit more than one test, but this one tends to be the easier one if it looks like this. So I could rewrite it like that. Remember, the rules of exponents tells me that if I multiply those two, I can add the exponents, right? So now, since p, which is the power here, is 3/2, and 3/2 is greater than 1, well, if it's greater than 1, then I know that it's going to converge by the p series. So at the very least, you got to know which test you're doing for sure. All right. On B, well, hopefully you can tell that P is 1/3, and 1/3 is less than 1. And if it's between 0 and 1, and 1/3 is between 0 and 1, then this is going to diverge by the P series. Right, even though, or the P series test. All right, on C, same thing. This P is equal to 1/4, which is less than 1, and therefore that's going to diverge by the P series test. Nope, sorry, I just hit that with my hand. All right, on D, or an example D on this one, you can't really quite use the P series test. I wish they would have kind of put that in a separate place, but they didn't. So on this one, you can't really use that, but the other test that I can do on this is I can use the, I can use the integral test, because this is going to be a continuous positive and decreasing function, right? So remember, you have to have all those conditions for you to use the integral test. So remember, the integral test is just going to tell me whether this is going to converge or not. Okay. All right. So now, okay. Do I have to tell what the value is for the fun? I just have to tell if it's diverging or converging. All right, so now I'm going to write it like this. Let's go ahead and just jump straight into it. Limit as t goes to infinity. between 1 and t, or 1 over e to the x dx. I could rewrite this as, every time I write it, I hate it. I have to write the limit thing. I could rewrite it like this. And you can use u substitution where u is negative x and du is negative 1. So the antiderivative of that is just negative e to the negative x. Okay, so let's go ahead and plug that in here. Now notice that right here, when I take this, that's going to go to 0 because you have a negative exponent. Okay, so that's going to go to 0. So my answer on this would be 1 over e. So it will converge. Okay, now you don't necessarily have to do this unless it tells you to, but it turns out that this is a geometric function. You could actually rewrite the original function that I have up there. So again, this part, unless they tell you to, you wouldn't have to do it, all right? So basically the only way for us to determine the sum of a series right now is to use the geometric formula or the telescopic one. Okay, so I could have written this as where r is 1 over e. Okay, so therefore, since I know, I can actually find the sum by doing this. So if I plug in a 1, I would get 1 over e, so that's a1. And then the ratio is also 1 over e. So my answer would be 1 over e minus 1. And of course, I found a common denominator in the bottom and then keep, change, flip, all of that. So this is actually the sum right there, which it didn't really ask. It didn't really ask for that, but I just wanted to show you. All right, so let's go to example E, and I think we're down to, this was the last two examples. All right, great. So now on this one right here, we can use the integral test again because it's continuous. It's continuous, positive, and decreasing. All right, now the hard part about doing this is the fact that you're going to have to use, basically the hard part is to try to integrate this. Okay, now just a little polishing of our integration skills. Remember, when you have something like this, I could break this apart into n plus 1, n minus 1, and I can do the partial fraction decomposition. So right now, I know I'm going to have to integrate that, so I'm going to go ahead and do this ahead of time, okay? So we have a over n plus 1 plus b over n minus 1. All right, I will multiply both sides times the denominator on the left. So that would leave me with this. Okay. So let's see, if n was negative 1, that would leave us with 1 is equal to a times negative 2. So a is equal to negative 1/2. And on this side, 1, if I make n is equal to 1, so this would be b times 2, or b is equal to positive 1/2. Okay, so I'm going to rewrite this. I can rewrite it like this. Let's go ahead and write the limit as t goes to infinity out here. between 2 and t here, and we can go ahead and split this up. I probably should have put x's instead. Okay, so now dx and all this. So the antiderivative of this, if you use substitution, you'll notice that that's going to just be a natural log. And I can just pull that negative 1/2 to the outside. And this is sort of a good example of why you need to be careful sometimes, because originally when I saw this, I was like, well, there's no way that's going to converge, right? Because you put that in. But it turns out that you could combine, let me write it on here, by the rules of logarithms, right? I could rewrite it as this. And that is what I was not expecting. Oh, keep writing x. Fool. Remember, when you subtract, you divide. Okay. So now, let's see. And I can figure that out as between 2 and basically infinity. All right, so let's go ahead and write what we have then. If you plug in a 2 there, you're just going to get a 1 on top and a 3 in the bottom. All right, now, just pay attention to this part. So right there, when you plug in an infinity here, right? So I can actually just take the limit of the inside first, and that's sort of what I showed you guys earlier today. So I can just take the limit of the inside. Okay, now the limit of the inside, if you use the horizontal asymptote rules, that's going to be 1. And the natural log of 1 is going to be 0. So basically all of this goes to 0. So I do have an answer, which is this. Now, what does that tell me? Now, this is not the infinite sum, okay? But what it tells me, the integral test, which is what I just did, it tells me that this sum is going to converge. Okay, that's all it tells you. It doesn't tell you anything else. It just tells you that this sum right here will converge to a single value eventually. All right, so let's look at f. So really, again, this is probably a pretty tough one to know what's going on. I did have to plug it in my calculator, and it turns out that it is continuous, positive, and decreasing. Okay. Now the question is, how would I take the integral of something that looks, well, like that? Ugh. So a lot of those are taking opportunity to dang it, I wrote in. They're really taking opportunity to really make sure that you're good on your integration skills. Now, this was a tough one, okay? But what I figure out is if I make u be equal to the natural log of the natural log of x, then du, remember the derivative of a natural log is 1 over u. In this case, u is the natural log of x times the natural log of x. Excuse me, times the derivative of the natural log of x, which is 1 over x. So essentially this right here is 1 over x natural log of x. All right, so here's the deal, dx. All of this right here is du. Okay, and then this part right here is going to be u. So just make sure what I'm about to do here. I'm going to go ahead and write the limit as t goes to infinity of 3 to t of basically just 1 over u. That's all I have left, du. All right, everything else got taken over. And that looks like a y. Oof, that looks terrible. I'm sorry. Okay, so now we're going to take the antiderivative of that, which we know is just the natural log again. Okay, so now we have just a very lovely solution here for this, which is the natural log of u. Now, u happens to be this. This is the natural log of the natural log of x. So yes, I agree with you. This is pretty much terrible. I'm going to write that on a different color just because I'm running out of room here. Let me erase this brackets. Maybe that's too confusing. Let me switch into parentheses here. And now I have to figure this out between 3 and infinity. Okay. Now let's see what we have here. There's really not a whole lot of, I can't really use the rules of logarithms there to do anything at all. I can't really simplify more than I already have. So at this point, I'm just going to plug those numbers in, all right? Oh my gosh. This is so stupid. The natural log of the natural log of the natural log of x. Oh. Just switch that for fun. That's so dumb. Minus the natural log of the natural log of the natural log of 3. Okay. So long story short is that this right here, if I were to plug in an infinity, that makes this infinity no matter what I do. So therefore, the natural log of the natural log of 3, infinity minus the natural log of the natural log of the natural log of 3 is still going to be infinity. Okay, so therefore, because the integral diverged, the sum is also going to be diverging. All right, at the very least, guys, there's not a whole lot to think about. It's very process oriented. So I guess we'll see you next time. Let me know if you have questions.